Hello, I am Francesca Trenta, PhD student of University of Catania, and today I will present this work about detection and classification of pollen grain microscope images. The research has been carried out thanks to the collaboration with Ferrero HCO that financed the project and allowed the collection of aerobiological samples from hazelnut plantations. Pollen identification and classification is an expensive process, which involves observation and discrimination of features by qualified experts. For this reason, there is an increasing demand to automate specialized tasks that usually requires human involvement in order to reduce processing time. Moreover, microscope images present high variability in the number of objects, noise, and occlusions. This made the segmentation of pollen grains a challenging task. In this work, more than 13,000 objects from aerobiological images were segmented under the supervision of experts. They collected the airborne samples. The acquired images were affected by a heavy background noise, including dust and bubbles. For this reason, we developed a segmentation pipeline to locate and extract objects from the microscope images. We collected a RGB image for each extracted object with 84 by 84 resolution, alongside its binary mask and patch with green background. Experts in aerobiology have labeled segmented objects, grouping them into 5 categories. Considering the small number of observations, we didn't include in our dataset for experiments the object of class 5. Previous studies have investigated the problem of automatic pollen grain detection and classification, in which collected datasets have been used to evaluate the proposed pipelines. Two public datasets are the Daller's pollen dataset and Pollen 23E. The first contains a total of 1630 grayscale images. The latter includes 805 color images of 23 pollen species, with 35 images for each pollen type. Larger datasets have been proposed for the task of the pollen grain detection, such as the Ranzatos dataset. However, the number of grain in this case is just more than 3,000. The design pipeline consists of 3 main stages: pre-processing, segmentation, and mask post-processing. First of all, we designed a pre-processing pipeline with the aim of reducing background noise and improving the segmentation quality. We applied several image processing techniques such as mean shift algorithm, OTSU, and Gaussian filter. The object segmentation pipeline aims to maximize the pollen grain detection alongside reducing the detection of non-pollen ones. After changing the color space from RGB to HSV, we applied several morphological operators such as closing and dilation. Finally, we obtained the mask for each object. However, we developed a mask post-processing pipeline to improve the quality of mask. The output of the overall pipeline is composed of 3 patches: patch of pollen or debris object, patch of the depicted object with green background, mask of the depicted object. In our study, we performed pollen grain classification. We subdivided our dataset by selecting 85% of images as training set and 15% of images as test set. In the first instance, we considered a pool of machine learning methods such as SVM, random forest, AdaBoost, etc. In particular, we extracted the feature from images by using HOG and LBP. In the second instance, we used CNN architectures such as AlexNet and smaller vGnet. To further address imbalanced dataset, we considered penalized classification models for SVM and random forest to adjust weights inversely proportional to class frequencies in the training data. To evaluate the performance of each classifier, we used the weighted F1 score for quantitative evaluation alongside accuracy metrics. With regard to OG, our experiments have shown that the best classification results were obtained by using SVM with the RBF kernel. In this table, we reported the results in terms of accuracy and F1 score. We observed that RBF SVM achieved an accuracy and F1 score over 85%, with a gamma value of 0.1 and a C value of 100. Furthermore, MLP consistently held to a F1 score of over 84%, with an alpha value equal to 0.1 and a number of estimator equal to 300. Nevertheless, we observed that SVM with the RBF kernel did not have a significant classification performance when using LBP features. For the sake of comparison, we performed object classification by using two deep learning models, AlexNet and smaller vGnet. Considering that CNNs and deep learning models take advantage from a huge amount of data, we trained these two architectures considering two different settings for the training data. First, we trained the CNNs considering the standard dataset, composed by the patches depicting the pollen objects. In a second stage, we augmented the dataset by including the segmented version of the training patches, obtained by applying the segmentation mask and padding the background with green pixel. The table details the accuracy and F1 results on the test set every 10 epoch, considering the standard and the augmented dataset. AlexNet outperforms the standard machine learning approaches only when the augmented dataset is considered. Smaller vGnet, trained on the augmented dataset, outperforms all previous approaches, reaching an accuracy of over 89% and a F1 score of over 89% after 20 epochs. The figures show the performance plot related to the training of AlexNet, considering the standard and the augmented dataset. It can be observed that the use of augmented dataset, besides improving the model performances, helps in maintaining more stable loss and accuracy fluctuation over the epochs. With regard to smaller vGnet, we observed also in this case that the use of the augmented dataset improves the model performances. In our experiments, we observed that both AlexNet and smaller vGnet classify pollen objects with a high confidence score. With regard to AlexNet, it tends to classify accurately the object of category 1 and 2. However, it tends to misclassify pollen object of class 1 and class 3. This misclassification is due to the similar texture of this object. Moreover, we observed that objects of class 2 sometimes are classified as objects of class 4. Smaller vGnet present the lower accuracy and F1 score when applied to objects of class 1 and 2. Also, he tends to misclassify objects of class 2 and 4. However, under challenging conditions, smaller vGnet achieved more impressive results than AlexNet. In this work, we presented a large-scale pollen image dataset. In particular, this work is meant to support the research on automatic pollen grain classification. In our future works, we are planning not only to improve the segmentation pipeline, but also define a proper deep learning architecture to achieve more accurate classification results. We organized a pollen classification challenge, which has been accepted at ECPR 2020. We request to participants to perform the object classification by using our proposed dataset. For further information, please see the reported links. Thank you for your attention.